First of all, thank you very much for inviting me. It's a pleasure indeed. And the first two talks here really set the stage for what I'm going to talk about, what I call the energy efficiency, not just by hardware, but truly in the sense of a co-design. So I know enough about process technology to be dangerous, but I'm really a circuit guy. But I know nothing about software, and that's why I talked to John quite a bit, and I've learned quite a bit from the system guys, and that gives me the qualification as to why I can talk about it. So this is what I'm going to talk about. I'm going to talk about the computation roadmap, the technology outlook as we see it to get the computations, then the challenges and the solutions being a hardware designer from the hardware perspective in compute, the memories, and the interconnects, and then to realize these solutions, why we absolutely need to do a co-design, and I'll stress as to what are the hooks that we need in the hardware and need to work closer with the systems folks to realize these solutions, and then I'll summarize my talk. So here's a compute performance roadmap. If you look, every 10 years we have increased the total system level compute performance by 3 orders of magnitude, from giga to tera to peta. And at this rate, at the end of this decade, like John said, we need an exascale performance, not necessarily exaflop, but 3 orders of magnitude increase in the performance itself of a system. So why am I interested in it? Simply because 10 years later, it goes into the clients, and then it becomes really into the things like handhelds and becomes ubiquitous. So my aim is high to see how can I get exascale performance so it becomes ubiquitous 10 years later. So let's look at how did we get here. From giga, how do we go to exa? And what did we do from giga to tera and from giga to peta? If I look at the transistor as a workhorse of delivering the performance, what this shows is the relative frequency of the transistor. You can see from giga to tera, the performance increased by 30x. From giga to peta, the performance increased by 250x. Lately, the transistor performance has flattened out. At the same time, if you look at the system performance, it has increased by 3 orders of magnitude, meaning that this is your transistor performance versus the system performance. The delta has come from parallelism or concurrency. 36x, 4000x. At this rate, when you go to the exascale that John wants, it's going to be 2.5 million times increase in the concurrency itself. Well, look at the power consumption. If you look at the power consumption, the gigascale machines were kilowatts, terascale machines were about half a megawatt, the petascale machines are 1s or 2s of megawatts, exascale machine will probably be gigawatt. Well, so the system performance increases faster, parallelism continues to increase, and that's the way we are going to get the system performance. And then the energy and the power will continue to be a challenge. So this is just to show you the landscape if you don't do anything. Let's go back and take a look, since this is the energy symposium. Where does the energy get consumed? Very rough. This is very rough. Let's take a teraflop system today. For a teraflop system, where does the energy go? It takes about 50 picojoules to do a floating point operation. That's 50 watts. Then you add memory. 1.5 nanojoule per byte. This is DDR3 or DDR4. That's about 150 watts. You add some communication cost of 100 watts. Then you add the disk. It takes about a 1 kilowatt. That means 600 watts or so goes into things like instruction decode, the control, the address translations. And truly, as I see it as a circuit designer, sorry, Michael, but it's a bloated with inefficient architectural features that were carried them through since the 70s. We've been just adding them in, and whether we use them or not, we've been carrying them with us all along. The goal here is to bring this down to something like 20 watt. Where does this came from? Goal. 1 kilowatt going down to 20 watt. This was inspired by a program from DARPA a few years ago called Ubiquitous High Performance Computing. And the vision of this program was as simple. They said, well, give me an exascale machine instead of a gigawatt. Give me a 20 megawatt exascale machine. If you can give me an exascale in 20 megawatts, means you can get me a petascale machine in 20 kilowatts, so our Air Force can put them in the airplanes. Today, a petascale machine is a big building. Well, then the army said, I can put a 20-watt terascale machine, and this is where my interests come in. I can have a terascale machine in your laptop. Well, it can go further. You can put this in your cell phone, 100 gigascale machine. Well, the NSA would really like a 20 megawatt, 20 milliwatt gigascale machine spying on you. Well, you could also have a megascale machine in your heart, under 20 microwatt. So you can see the energy is the challenge, and here the important thing is you have to bring it down to something like 20 picojoule at the system level, not at the transistor level, but at the system level, including software. So how do we get there? So I'm going to look at three things.
Can I just ask what units? How could it be joules? Don't you need some performance to go with the joules?
And that is the operation. Per operation. It's 20 picojoule per operation amortized over the system performance. So if I look at the process technology, it's going to come to rescue a little bit. The density, I hope, will continue to increase. This is the Moore's law. The frequency has already flattened out. The supply voltage scaling has flattened out. And as a result, if I look at the energy scaling in the process technology compared to ideal, there is some. And I'm going to take that. I'm going to use some of that. If I look at the very fundamental operation, a compute operation, what this shows is different process technologies, all the way from 45 to the projected 7 nanometer. What does it take to do a floating point operation, to fetch the operands, to access one bit from the DRAM, and to communicate one bit to the neighbor? It costs about 275 picojoules in 45 nanometer. It will go down, this simple operation, to something like 60 picojoules by 7 nanometer. If it is 60 picojoules, it's 60 megawatts. So by the process technology itself, I'm not going to reach my goal. And this doesn't include anything else, no overhead, nothing, just a simple operation. So what I've got to do is, like John mentioned, I have a knob called voltage scaling. And this has been researched quite a bit. It's very simple. You start scaling the supply voltage. As you scale the supply voltage, your frequency of operation goes down. Your total power goes down. Your leakage power increases some. But if you look at the energy efficiency, in terms of the energy it consumes to do that operation, that energy efficiency improves significantly by an order of magnitude. So this was experimentally shown, called the near threshold voltage. And this was a simple processor that was built on 65 nanometer process technology. And what you see here is the supply voltage scaling versus the frequency going down on the y-axis here, and the total power goes down here on the y-axis on this side. Well, what this shows is for this particular processor, as you scale the supply voltage, this is the energy efficiency in terms of ops per watt. This energy efficiency increases, it peaks at the threshold, and then in the subthreshold region, it starts falling down again. So clearly, the energy efficiency improves by almost an order of magnitude. Well, there is one little detail that people don't see, which is this. Your total power has reduced by 4 orders of magnitude, whereas your leakage power has reduced by only 3 orders of magnitude. Meaning, your leakage power starts becoming a substantial portion of your total power as you start reducing the supply voltage. Well, I'm coming to this theme. If you know how to control this, I don't know how to control this in hardware. Now the software becomes really important. If the software can manage the active versus the leakage power dynamically. Today's software doesn't know how to do this. And I'll come to that later. Now, to understand this, we really did an experiment. This is what we call an experimental NTV processor. This is the old Pentium, circa 1992, original Pentium. Took that Pentium, we resynthesized it on a 32 nanometer high-k metal gate process. And you see this here. This is on a new FPGA. It's a new package. And we had to build a custom interposer because the old motherboard, as you see here, this motherboard, we couldn't find one. We had to get it on eBay. Don't ask me how much we paid for it. It's an old Pentium motherboard from eBay. And we had to build an interposer. We put this interposer, and this system with a legacy Socket 7 motherboard booted Linux and Windows. It worked. So we characterized it. When you characterize it, this is what it looked like. It's an NTV processor. You can have high performance. You get the full voltage, you can have it 1.2 volts, it runs about a gigahertz, consumes just less than a watt, and gives you 1200 MIPS per watt. At the energy efficient point near NTV, at about 450 millivolts, it runs at 60 megahertz, 10 milliwatts, and look at the energy efficiency, 5800 MIPS per watt. And if you want really low power, you can go into this region to about 2 milliwatt, but again the energy efficiency suffers. Notice one thing, the original Pentium was 60 megahertz and consumed 15 watts. With NTV, it's consuming 10 milliwatts. So I have a knob in hardware to improve the energy efficiency on the fly, dynamically, if I can use it. Hardware people don't know how to do this dynamically. That's where the software comes in. If the software is intelligent enough to know when I need the performance, when I need energy efficiency, when I need low power. So, some observations here, some other details. The same processor, sub-threshold, near threshold, and full VDD. Where is the power going? Dynamic logic, logic power dynamic, logic power leakage, memory dynamic, and memory leakage. If you look at this Pareto analysis, you can see this is the logic dynamic power. You look at the logic leakage power. As you go towards NTV, the logic leakage power becomes a substantial portion of the total power. You look at the memories. You look at the memory leakage power here. As you go into the sub-threshold region, your memory leakage power becomes substantial. With this kind of a dynamic behavior of energy consumption, it's really difficult for hardware to control it, and we really need hardware-software co-design to control this. This brings to the next point. Well, I know how to control the power and the energy potentially given the hardware-software co-design. But that also means that I need to bring the power delivery closer to the load, and hence the integration of power delivery. If I can bring the power delivery mechanism closer to the load, then I can control that power delivery mechanism quicker in nanoseconds as opposed to milliseconds today, and I can reduce the energy consumption. So we built an integrated test chip here. This is the converter chip, and this is a load chip. And if you look at the energy efficiency of such an integrated voltage regulator, it's pretty high. It's of the order of 85% or so. And it can really improve. This was a test chip. So the power delivery really needs to be brought closer to the load for not only for improved efficiency, but also for fine-grained power management. Again, we can do this in hardware. The technology exists. Only if the system software can control this at that level of granularity. And hence, working closer with the system software folks is really important to improve the energy efficiency of the system itself. Now, let's switch gears. That was a compute. What about the memory technologies? So we said, well, right now it takes about 75 picojoule to access one bit at the system level from DRAM. That's 75 megawatt for an exascale machine. We need to bring that down to something like a 1 or 2 to make it affordable. So we said, let's look at the different memory technologies. So we looked at various memory technologies: SRAM, DRAM, flash, phase change memories, spin torque, ferroelectric memories, MRAMs, resistive memories. And if you look at, I'm just going to cover this in one slide. This takes probably 2 hours to go through the details, but I'm just going to give you the report card. If I look at the technology node in terms of maturity, considering the half pitch that's being used, you cannot beat SRAM, DRAM, and phase change and the NANDs. You look at the memory cell size. SRAMs are huge. DRAMs, flash, and PCMs are relatively small, fairly very small. If you look at the density, you cannot beat the density of the flash. Even the PCM cannot beat it. If you look at the cycle time, SRAM is the fastest, followed by DRAM. If you look at the energy per bit, SRAM is the most energy efficient, followed by DRAM. And then if you look at the endurance, you cannot beat the endurance of SRAM and DRAM. PCM and FERAM, and the flash have the lowest endurance. Putting it all together, 10 years from now, if we are going to build a system for Lawrence Berkeley lab, My bet right now, by looking at it, is the DRAM for the first level for the high capacity memory, followed by NAND and PCM as the next level storage, simply because of the maturity. That doesn't mean that the other technologies are not there. They are just not mature enough today. So I need to go polish DRAMs. I'm going to take 75 picojoules from the DRAM and bring it down to 1 or 2 picojoules. What do? I need to do two things. I need exponentially increasing bandwidth, and I need exponentially decreasing energy, picojoule per bit. So when we look at it, you look at the traditional DRAM. The traditional DRAMs have had the RAS and CAS, row address stop and column address stop. Why? Because in the early 80s, your package had 16 pins. The pins were expensive, and you had to put in a 20-bit address into a 16-pin DIP. So you had a row address strobe, which came in. It accessed a bunch of pages. You read all these pages into the row buffer, followed by you had multiplex column address strobe. It went and read a few bits from this row address, from this row buffer, and put them onto the bus. Look at the wastage that you had. And this is the same architecture that we have been carrying it through for decades. We need to change this by having a new DRAM architecture such that the address comes in, you access only the page that you need to read, and then you read it out, and all the data that has been read from the DRAM gets utilized. The only problem is this requires a lot of pins. Well, the technology to your rescue. This is where the 3D integration of DRAM and logic comes in, where you have a package, you have a logic buffer chip, and using the logic buffer chip, you have a technology that is optimized for logic and for the I/O signaling. You put in a stack of 3D DRAMs, and this is a DRAM technology that's optimized for lower cost and memory density. And this was an experiment using the 3D that was done by Micron called Hybrid Memory Cube, and we worked with them on this one. And what this showed is you could indeed improve the bandwidth by almost an order of magnitude, from 10 today to something like 128 gigabyte per second, followed by, if you look at the energy, 50 to 75 picojoule going down to 8 picojoule per bit. So I'm there, not quite yet, because I cannot put 8 megawatts into my exascale machine or 8 watts into my terascale machine. I need to take it to the next level. Changing gear. So I talked about compute, talked about memory, now comes the communication. And you guys talked a lot about the communication. This is where the problem is. The other two I know how to handle. It's very simple. Energy per bit in communication on the y-axis here, it increases with distance. We know this. On die, with the chip to chip, board to board, and between the cabinets. Well, one of the biggest problems is the sizes of the systems are not changing. Your transistors are scaling, but my size of the chip approximately is remaining constant, 15 millimeter on the side on an average. My cabinet size is remaining constant, the same size of the cabinet. So the distance over which you move data doesn't change from generation to generation. The dielectric constant doesn't change. What's the best you can get is 1, right? You can't go to below 1. So as a result, the energy that it takes to do the communication over the same distance doesn't really scale much. And that's what I'm showing here. Let's look at on-die first. On-die, what this shows is technology generations versus this is relative. If you look at the compute energy, because of the dimension scaling, it's scaling really well. But if I look at the on-die interconnect energy per millimeter, that is going from one corner to the other corner of this constant chip, it doesn't scale well. 6x versus 60%. So the interconnect energy will start to dominate. We did some experiments. Network on a chip. For example, here was a network on a chip on an 80 core teraflop chip done a while ago. And this showed about 30% of the power goes into the network. The 48 core single chip cloud chip. On this one, about 10% goes into the network. But the percentages are misleading because a lot of power goes into the cores in this particular case. So we started looking as to what is going on. This shows a very simple interconnect analysis. What this shows is on chip, this is your on-die interconnect length in millimeter, And this shows the delay of the wire, a repeated wire, on the y-axis. And you can see that the delay starts increasing as you increase the distance. The energy of moving the data across this distance is this yellow line over here. When we build networks on a chip, we have a switch or a router on the chip. And then that router has a delay. It's a switch delay, which is constant 1 or 2 nanoseconds. What this shows is if that delay is 1 or 2 nanoseconds, then it doesn't make any sense to put a router on a chip less than 6 millimeters from the delay considerations. This is the energy of the switch. What this shows is if it is less than 16 millimeters, it doesn't make any sense to put a switch on the chip. So the bottom line is use the wires in the chip as very simple buses and don't create unnecessarily exotic architectures to do the communications. And we know that the cores on the chip in the future will definitely be less than 6 millimeters, meaning go to the old-fashioned buses. Connect them using simple buses, and you'll be more energy efficient. So in the future, the interconnect structures that we need to start looking at are something very simple. You have cores connected together, you have a shared bus, then you have shared memories, or you can have crossbar switches if you want to connect these things together over a longer distance. Or if the distances are too large, only then start thinking about packet switch networks. Followed by on the board, and I'm going to talk about the cabinets and the system next. So you're going to have hierarchical and heterogeneous networks, all the way buses to the clusters to the next level of buses or packet or hierarchical switch networks. So a simple network that we are used to with a bisection bandwidth having a mesh or a torus at the system level is not going to cut it. And that's an active topic of research being followed. Let's go beyond the chip. Electrical interconnects. How do I connect these chips together? Less than a meter. If I look at over the last several years on using the ISSCC papers, this is the energy per bit on the y-axis and the data rate in gigabit per second. Energy per bit has been going down. So today, less than a meter, I have pretty much a sub-picojoule per bit energy. If I look at the bandwidth, it's also increasing. Unfortunately, the bandwidth and the energy is improving, but not enough for what we need. So the electrical interconnects, their advances are really based on employing new low-loss, non-traditional interconnects, such as top-of-the-package connectors. They're willing to spend a little bit more money onto this. Low-loss flex connectors or twin-ax cables. Using this, what they have done is they have really pushed the energy in picojoule per bit. This was the state of the art, and now they are something like 1 to 2.5 picojoule, even over 3 meters. And you can see the eyes, they're still wide open. So clearly, in the interconnects, they have started doing co-optimization. The silicon people just don't do interconnects without co-optimizing. So the circuits and the co-optimization of the circuits and the interconnect components is important, and it's happening. Greater than 1 meter. Optical interconnects, because you cannot really go electrical greater than 1 meter. Where does the energy go? If we really go, and this was the source is the Peat study group that was formed a few years ago, the energy, this shows, let me spend some time over here. This is the laser efficiency. This is your telecom laser. Between 1 to 10% is the laser efficiency. If I look at, in the future, what is a picojoule per bit of the total optical interconnect? It's of the order of 10 picojoule per bit. Where does the 10 picojoule go? Almost 9 picojoule goes into the laser. The electricals are not that energy expensive. If the energy efficiency of the laser increases to 10%, it goes down, as you can see. There is another factor to this. Lasers cannot be turned on and off as quickly as you think. So it really also depends on the link utilization. 100% utilization of the link, your energy efficiency is 10 for 1% laser efficiency is 10 picojoule. If the utilization drops, energy efficiency reduces. It goes only 10%, as in a realistic case where the data traffic tends to be bursty. potentially the energy efficiency of optical interconnects can be really low. So you need to consider, as a system designer, that the energy in supporting electronics is very low. The link energy is really dominated by laser. So a lot of innovation, a lot of research is required in the fundamental lasers. And at the system level, utilize optical interconnects only when the link utilization is high, such as connecting cabinets together where the data aggregation happens. So let's create a straw man just on a piece of paper, an exascale interconnect. Assume I got a 40 gigabit per second, 10 picojoule per bit, $0.50 per gigabit per second cost, with 8 byte per flop data movement. How will I build one? Let's say 0.8 petaflop machine. I make the UHPC vision come true. I got a cabinet with 0.8 petaflop. Put this in a cluster of 35. Put 35 such clusters together. Now to connect this together with these optical interconnects, 1,000 fibers each connecting to this first level optical switch, 8,000 fibers each. All this costs $35 million and will consume 217 megawatts in optical interconnect only. We don't have power, we don't have money, we don't have that kind of power to waste. So clearly, we got to go do some system, hardware, software, co-design over here. What that means is bandwidth tapering. And I think both of you talked a little bit about this, about the bandwidth tapering. What that means is you can't afford it. If you can't afford it, you have to go restrict it. And this shows, it's a complicated diagram, but the different levels of hierarchies, all the way from the core to the first level, second level, chip level, board level, cabinet level, system level, and the amount of data that you're going to move per operation. This is what John wants without any tapering, right? This is what we want. Start with the 24 byte per operation at the ALU level and then start tapering it down very naively. Well, this costs you 217 megawatts. This is what I can afford as a hardware designer, which is of the order of 1 megawatt or 3 megawatts. Somewhere in between is the truth. Right? What that means is I can build some hardware in between. I can only do that only if the software can make use of it. So the software has to be intelligent enough that it can taper the bandwidth carefully. So this is where the hardware software co-design comes in. In the past, what we have done is started with the application and say, let's go build a hardware. Okay, so where we started? I'm saying, no, you got to go both ways. You got to understand the underlying technology, look at the limitations, the issues, and the opportunities that you can exploit. So the bottom of guidance from the circuit designer is very simple. You can use NTV, but it comes with its own problems, and I need software to handle this, such as variations. NTV is very limited. It cannot be applied to the arrays. There is a disproportionate amount of energy in interconnects versus the compute. The leakage power starts becoming disproportionate. The DRAM scales, energy scales, but not as much. And finally, the system level interconnect is really limited by the laser. These are the 6 major bottom-up guidances that we give. So if you look at the strawman architecture for something like NTV, you can apply NTV and you can take the 600 watts down to something like 37 watts. At 15 picojoule per flop, you're very close. You're coming very close to the goals that the UHPC has had. The software-wise, the challenges are simple. You got extreme parallelism, 1000x, simply because you're going from peta to exa, and 4x increase because you're going to use NTV operation. Data locality becomes very important. Reduce the data movement. You need intelligent scheduling. Today's schedulers and system software are fairly dumb. Sorry to use the word dumb, but all they look for is what's available and schedule a thread. That's not what we want. Like you said, we want asynchronous scheduling, which is introspective. There should be fine-grained resource management, and we need to really rethink some of the algorithms. So I'm not going to go through the laundry list of the programming and the execution model, such as the asynchronous event-driven tasks, new programming model with separation of concerns, the new execution model with dynamic event-driven scheduling. But really, The vision that I see is you have an over-provisioned system, and the system software introspectively does the resource management, such as you've got lots of cores, and there are lots of cores with variations. If you are going to run this near the threshold voltage, the variations are going to increase by an order of magnitude. So the software needs to go and decide what thread you're going to run where. You can do the fine-grained resource management, and also in the hardware we can have sensors so that the system software can do the introspection by looking at where am I today. It's also called sometimes self-awareness. Clearly, we need schedule threads based on the objective and the resources, dynamic, sensors, and the system software to implement this introspective execution model. And that's why nowadays you don't see me in the process community or circuit community. I spend a lot of my time with the software and the system folks to see how we can make an impact here. So finally, this is my summary. Power and energy. We talked about the NTV. We talked about the DRAM and the 3D integration. Communication energy will exceed the computation. Data locality. We need a revolutionary software stack. And truly a hardware software should not just be a buzzword, but we need to do something about it. Thank you very much.
Sorry, what did NTV mean?
It's near threshold voltage.
Oh, right, okay.
I have to ask the speakers to keep the acronyms under control. Go ahead.
I particularly like the idea of moving the thread to the data rather than the data to the thread. So that goes very well with the location-centric model, where it might be more cost-effective to move the thread or the computing algorithm to the data rather than the other way around. But for that, we have to be able to reason about this up front to see which one of them is actually more effective.
And that's I agree with you, and that's one of the reasons the system software has to be cognizant about where is the data and where is the thread. Today, it doesn't do that.
So I have a question about the Pentium example, a fascinating example. If I understand what you did, you remanufactured a Pentium using today's technology. And the performance was almost the same, but the power requirements were greatly reduced. Is this equivalent to saying we have the power of Pentium in our cell phones? What does this mean?
It means that if the original Pentium was good enough, what you were doing, all you have to spend is 10 milliwatts today with the process technology that we have, right? Instead of 15 watts. So
we have improved things considerably over the past 20 years.
And we are also increasing inefficiencies because of our software stack and the architectural advances for programmability. And those inefficiencies are causing a lot more energy consumptions. We need to identify those and correct them.
Okay. Question out there.
You mentioned the NTV operation, and you showed us that there is an optimal value of the voltage, and afterwards it decreases the efficiency, computational efficiency. Is this due to the presence of errors, due to the low threshold voltage?
Well, what happens is, as you go below the threshold voltage, the drop in frequency is faster, right, than the drop in the energy. So your energy per operation really doesn't go down as much. There are two exponentials that you're fighting.
Let's see. Is there another question out there? Go ahead, please.
How does the NTV compare to the nominal voltage of a process?
Well, the nominal process voltage is whatever the process is optimized for. Then there is what's called Vmin. And Vmin is the voltage at which a simple storage elements such as 60 SRAMs, they operate reliably under different variations and under different manufacturing conditions, right? NTV is going beyond that. And it's not free. You have to go and design your circuits with the NTV in mind. So just to give you an example, if the process is at 1 volt, the Vmin is typically 0.7 volts. So you'll see the commercial parts, like your laptops, processors, they run at 0.7 volts. But we are talking about going beyond that. Towards the threshold is 300 millivolts, going to something like 400 millivolts, 450 millivolts. Very, very close to the threshold. So the overdrive between V and VT is very small. And what that tells you is the small variation in VT is going to have a very large variation in the frequency.
So I have a different way of thinking about it. Can you tell me if this is right? I look at the voltage, and at 0.3 of a volt, the Boltzmann factor is e to the minus 12. And that gives me an on-off ratio of about 1,000,000 to 1, which is what I need to turn the transistors off and not have too much leakage.
Mm-hmm.
So is that the reason why the NTV tends to cluster just above 0.3 of a volt?
Well, the only difference is here I'm not talking about changing the process technology or a VT. Because you could argue that I'm going to create a process with a Vmax of 0.5 and VT of 100. On a piece of paper, that's fine, but you really cannot manufacture such a thing. Right? So I'm not talking about ion to I-off. Ion to I-off remains the same, but my ion reduces by about 10x.
Okay. All right. If there are no questions, let's go to break, and let's thank Shekhar again.
Thank you.